So, welcome to this course, Learning Physics through Simple Experiments. This course is very different from the traditional courses because it is not meant for some particular examination or to tell some particular syllabus or equations or formulae like that. Nature is beautiful and the nature is governed by certain principles, and we want to understand those principles. And to understand those principles, nature displays varieties of events and phenomena, and based on those we have to understand physics. All our equations, all our formulae, all our derivations are essentially an attempt to understand these basic principles on which nature displays its events. So, we design some of our own experiments so that those rules, those phenomena, those equations, those concepts are understood in a better way. So, this particular course is just to show some experiments, simple experiments, self-designed experiments you can also design, and then see how physics is working there, and from that develop a deeper understanding of physics. So, this is about the course. Now, the participants you have registered, and I do not know how many of you are students, how many of you are teachers, how many of you are very senior teachers, senior than me. So, it is a mixed audience and I do not know how do I address. So, I am coining a word, you are my physics loving friend, physics loving friend. So, I will call you PLF. So, all my PLFs, welcome to this course. I have divided this 8-week course in 4 broad modules, although in experiments you cannot really divide things. All these divisions in chapters is artificial. When you are doing something, then many of the concepts go together in one experiment, but still broadly I have divided it in 4 parts, that is optics, that will be our first module, and then mechanics, and then electricity magnetism, and then oscillations and waves. So, roughly 2 weeks on optics, 2 weeks on mechanics, 2 weeks on electricity magnetism, and 2 weeks on oscillations and waves. So, we will start with our first module, that is optics, light. Very simple, light. And the day someone comes to this planet and opens eyes, the interaction with light starts. And after that we experience so many things about light, we learn so many things about light, and then theories are developed and all other phenomena are there. Now, what is the first thing that is taught when a chapter on light starts in schools? Perhaps the first thing is light travels in straight lines. So, we will also start from that. And how do we know that light travels in straight lines? We can do certain experiments. So, you have a bulb glowing, you can see it. Put some object in between your eyes and the bulb, and what happens? I am not able to see the bulb. Why? This simple experiment tells me that light travels in straight lines. Light falls on this card, this paper, therefore it is not able to reach my eyes, and therefore I am not able to see. But does light really go in straight lines? We will come to this question. When we say that light travels in straight lines, this is an approximation. First thing is, we mean a homogeneous medium, transparent homogeneous medium, only then the light travels in straight lines. And if the medium changes, the refractive index of medium changes, light can bend. mirage is one example, and many other examples. The approximation in which you can represent light by straight line paths is known as ray optics approximation or geometrical optics approximation. In this approximation, light casts shadows. When you walk in sun or under the street lights, you can see your own shadows on the road. So let us make some shadows. Let's do this experiment. Let's make some shadows. So again this bulb. Alright, now I will be making shadow of this pen, and you watch for the sharpness of the shadow. Look at the shadow, quite sharp, rectangular. I am increasing the distance of pen from the wall and see how the sharpness is changing. It is quite diffused now, very diffused, very diffused. If I go close to the wall, it is quite sharp, rectangular. If I go away from the wall, then it is a totally diffused kind of shadow. Now it will be your task to explain all these phenomena, this intensity, this diffuseness, in terms of the path of light rays or straight line paths that light takes. One more observation, keenly watch. I am rotating this bulb now. The shadow is very, very diffused. I am rotating the bulb, and you see what happens to the shadow. See how the shadow is changing. I have rotated it almost 90 degrees. Go back, and this is the shadow. Rotate it, rotate the bulb, and this is the shadow. So this also you have to explain why the shadow is changing its character when the light bulb is getting rotated. Now to give you a clue, I will show you the bulb, and you see what happens when the bulb is rotating. Look at the bulb, it is a structure inside this glass. Now this is the initial condition, and now I will be rotating it through 90 degrees. So I am starting the rotation. So just watch what kind of changes you see. I have almost rotated it by 90 degrees. Going back. Okay. So I hope this helps in explaining what happened to the shadow with rotation of bulb. So I have this cardboard, and in this cardboard I have made a hole, and if you see the shape of the hole, it is in the shape of this sign of plus. The intention is I will let sunlight pass through this hole, this opening, and on the other side I will collect that light and see the pattern that light makes. Similarly, I will have more cardboards with different shapes. Okay, so Ranjit is holding the screen, and sunlight is passing through this hole, and on the other side it is going and making a pattern on the screen, and as expected, the pattern made by the light on the screen is also in the shape of that mathematical plus sign. Now see what happens if the screen is taken away from this opening. So Ranjit is taking the screen away. You can see that the boundaries are diffusing, and and by now it is difficult to recognize that there was a plus shape, and now you can see at this distance it is almost a circular disc. The opening is in the shape of plus sign, but the light that falls on the screen going through this same opening is making a circular disc on the screen. Let us change the shape of the opening. This opening is diamond type parallelogram, and if you see on the screen you have that diamond shaped spot. And now Ranjit, take away the screen, increase the distance, and you see you don't recognize anymore that parallelogram type diamond type shape, and once again it has become a circular disc. One more shape. This you can see, it's a kind of a rectangle, nearly rectangular shape of the opening and nearly rectangular shape of the pattern made on the screen by light passing through this rectangular opening. Now take the screen away. Okay, still you can see it is rectangle, boundaries are diffusing, and by now it has become a circular disc. You can see the periphery of that spot, it's circular. So independent of the shape of the opening, your final spot is bright circular disc. So why that spot becomes circular once the distance between the screen and the opening is large, independent of what is the shape of opening? That bright circular disc is in fact image of the sun. The sun's disc is circular, and therefore this is also circular. But when you bring this screen closer to this opening, then it is the opening that decides what kind of shape will be there of the bright spot. You can understand it if you do little bit of drawing. Suppose in that opening you only have a single point opening. What will happen? Wherever you place your screen, that sun, that disc will be imaged as a circular disc here at all distances, if it is a single point opening. An actual opening can be thought of as a collection of these single point openings, and therefore each of this point will make a circle. Now if the screen is closed, all these circles are small circles. Suppose suppose your opening is triangular. So these are the points which are, you take these as the points. This is all triangular. Each point is making a circular disc, but if the screen is closed, those discs are small. So you have a disc like this, 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 and so on. So all this will be there. From each point you make circular discs, but then that triangular shape is still maintained. That triangular shape is still maintained. But if the screen is away and these circles becomes large, then if you make that drawing, you have centers here, but then you are drawing large circles. Like this. From these, what you will see is a round thing, a circular thing. So here it will be essentially the image of the source, and here it will be essentially image of the opening. Okay, now I will make shadow using a different light source. This is a laser light source and green light is emitted and it is going on the wall. The size of the beam is small. From the spot on the wall you can see how much is the size, or you can see it somewhere here. So, this is the size, and the obstacle that I am bringing is much wider than the size of the beam. This is opaque. So, if light goes in straight lines, then the whole beam will fall on this object, opaque object, and nothing will go there. So, let us see. Here it is. The entire light is now falling on this object, opaque object, and everything is blocked and nothing goes on the wall. So, light does travel in straight lines. Now, I will do something else. We will put an object whose size is less than the diameter of this beam. Now, we will be putting a thin wire in front of this light beam. So, and it will be thin. So, it will not block the whole of the light, only the light which falls on that thin wire should be blocked and other light should pass, and you can expect the shadow of a wire. So, we have fixed a thin wire on this CD disc, and you carefully see the central hole. On the vertical diameter of the central hole you can see the wire. And our plan is to send this light beam on this wire. So, from the sides light will go, and apparently perhaps we can expect that light will be blocked by this wire and a shadow will form on the other side. So, I will request Ranjit, my associate, to fix up this wire and this light source on some stand, so that light falls on this wire. This is the point directly in front of the wire, and wire is opaque, does not allow light to pass through. So, light should have been stopped there at the wire, and here you should have gotten a dark, but you have maximum intensity here, and then you see 1, 2, 3 on left side, 1, 2, 3 on right side, you can keep on counting. There are different zones of high intensity and then low intensity, again high intensity, again low intensity, and so on. On left of this bright spot at the center and right of the bright spot of the center. So, this is the shadow of a thin wire. So, what happened? When we used a pen, a pencil, varieties of objects in front of a light beam, light was partially blocked by the object and there was a darkness in front of that object. But here the things are very, very different. Light does not go in straight line paths in this particular experiment. So, when does light go in straight line paths? In what conditions I cannot use this approximation? For that, you also know that light is a wave, and there is something called wavelength of light. So, the openings or obstacles, size of these openings and obstacles and the wavelength, they will decide whether light can be treated as rays going in straight lines and stopping wherever an opaque object is encountered, or light will show some other character. And the rule is that if the size of the opening or obstacle is much larger than the wavelength. 100 times, 1000 times, 10,000 times, 100,000 times. Then you can treat this light as rays going in straight lines, and those straight lines you call rays, and we call this approximation as ray optics approximation. And that was the case when I used bigger objects to form shadows. But if the size of the opening or the obstacle is comparable to the wavelength of light 10 times, 15 times, 20 times, maybe 25 times, then the ray optics approximation will not work. We also call it geometrical optics approximation. We will be talking about reflection, refraction, all these things. They all fall under geometrical optics or ray optics, and will be valid only if the surfaces where the light is falling have dimensions much larger than the wavelength.